Now let's talk about how it does its magic. What we want is this. We have a mapping matrix that takes vectors from Rn and gives you vectors in Rm. It's a mapping from Rn to Rm. And let's say the rank is R. The mapping from the row space of this matrix to the column space of the same matrix is a one-to-one mapping. Any vector in the row space will give you a unique vector in the column space. So that is a one-to-one mapping. That's because if X is in the row space, and let's say it's a non-zero vector in the row space, then that is a linear combination of the columns of A. And as we saw from the very first chapter, I believe, linear combination is unique. You cannot get two different vectors by taking the same linear combination, and all linear combinations of the columns of A will find itself in the column space, because that's the definition of the column space. It's a set of all possible linear combinations. So one-to-one onto mapping, as it is called. Now, what we are trying to do is to find a basis in the row space. Suppose we can find a basis in the row space. Now, that is not very difficult to find. A basis would be just the pivot rows. I just take the pivot rows and take their transposes, so it will be column vectors. That would be a basis for the row space. And you want an orthonormal basis, not just any basis. Even that is not very difficult, because once you have a basis, all you have to do is to run Gram-Schmidt and you will get orthonormal basis. So that we can do. So starting from the pivot rows, we can actually get an orthonormal basis. If you take any one of these vectors from the orthonormal basis, so Vi will be one vector, one basis vector of the row space, it will end up as a unique vector in the column space. So you will get some set of vectors in the column space, but there's no guarantee that those vectors are going to be orthonormal basis of the column space. There's no guarantee. We'll just get some vectors. So what we want to have is an orthonormal basis in the column space. So let's take stock of what we have. So we have A applying on the orthonormal basis vectors of the row space, and we know that we will get some vector U as a unit vector, and sigma is the length of that vector. So every single vector that you have in the row space, and how many of them do we have? It's as many as the rank, because the dimension of the row space is the rank. So we have R vectors standing here, and applying A on them, we're going to get R vectors in the column space, and we can make sure that they are normal with their unit vectors called the normalization factors, sigmas. And exactly as we did in the case of eigenvalues, we can put those sigmas as the diagonal elements of a matrix. If you expand this guy, you will get this guy. So this is possible. So we can always write A V hat. I'm going to write V hat rather than V, because I don't have n vectors here. I have only R vectors here. So it's a smaller version. A V hat is U hat, and then sigma hat, because this is an R by R matrix now. We would like this U to be an orthonormal basis of the column space. There's no guarantee that it's going to be that. What we want is orthonormality on the column space side. The normality part, the fact that they are unit vectors, is very easy to do. We can just normalize it and take out the normalization factor and call it a sigma. So that is easy. But getting them to be orthogonal to each other, that part is not easy. We already have orthonormal basis in the input side, in the domain, in Rn, the row space, the space where X vectors live. And these vectors do span the row space, because that's the definition of the basis vectors. Now, suppose we actually want not just a basis for the row space, but for the whole domain, all of Rn. So what's left in the domain would be the null space. So remember, in our picture, on the left hand side, we have the row space and the null space. And if you have the basis for the row space and we add the basis for the null space also, then we get the basis for everything. Okay, so we can actually complete the basis by taking the basis for the null space also. And then V will be an n by n matrix, because we've got n linearly independent vectors. Those are the basis vectors for Rn, and we can choose them to be orthonormal, and that is possible. So that means V transpose is going to be V inverse, and we would like to have the same thing for the output side, the codomain, the column space and the space containing it. So that's what we would like to have. We have the transformation Ax equal to B, which will take vectors in the row space, two vectors in the column space, and the right hand side is Rm, that is all possible vectors on the output side, and Rn on the input side, the green side, that is all possible input vectors. So this is what we have. This is what we had right after we did our 4 fundamental subspaces some time ago. All vectors in the row space will end up in the column space. All zero vectors will of course go to the zero vector here, because a matrix times zero vector is going to give you 0. And on top of that, everything in the null space will also go to the 0 vector. That is the definition of the null space. We can take the example of the xy plane as the row space and the z-axis as null space. But most vectors in R3 are not going to be in the xy plane nor on the z-axis. It's going to be somewhere else. So those vectors are actually just linear combinations of vectors in the null space and the row space. So we have to worry about that in a second. But what we already have is an orthonormal basis for the row space, which we can always find because we just take the pivot rows as the basis and then orthonormalize it using the Gram-Schmidt process. We'll get an orthonormal basis there. So that we have. And we would like to have an orthonormal basis here also. We'll go to some vectors here, but we don't know that if those guys are actually orthonormal basis for the column space. Now, if you complete the basis in the null space, which we can do by finding the complete solution to ax equal to b, the free variables, etc., then we can complete the basis on the input side, the domain Rn. So we have n vectors there. Similarly, we can complete the basis on the left null space, and that way you can get a full basis for Rm also. That would give you the U matrix. So this is what we want. Now, like I said, most vectors in the input side are not in the row space nor in the null space. So that we have to keep in mind. So what we are